We present our work, learning the dynamics of compliant tool-environment interaction for Visuo-Tactile contact servoing. Our objective in this work is to reason over and control the extrinsic contact between a compliant tool and the environment, without requiring access to tool or environment geometries, relying only on sensor feedback. The goal is ultimately to enable contact-rich tasks, such as scraping objects from a surface while avoiding obstacles, as shown on the right. At the core of our method is a novel contact feature representation. We represent the contact first with a binary contact indicator, which represents whether the tool is in contact. Next, we have a contact geometry. We assume the geometry is a line in 3D space that describes the contact between the tool and environment. The contact geometry term is only active if the system is in contact. Finally, we have the wrench at the end effector of the robot. We propose a deep learning architecture to model how the proposed contact feature representation evolves given raw observations and actions. We then utilize this model for model predictive control. Given a desired contact feature trajectory to follow and percepts from the environment, the method yields actions that servo the extrinsic contact as desired. We train our method using real-world data with self-supervised contact featured labels collected on tools with varying geometries and physical properties. We collect data using random actions to cover a diverse set of contact features. We apply our proposed contact controller to two experiments. The first experiment examines the method's ability to control contact in the obstacle-free environment. We specify diverse, desired contact trajectories for the controller to realize on the tabletop. Here we show multiple results for our method. Our results show our controller is able to accurately realize desired contact trajectories. This includes cases where the tool must be tilted to realize contact geometries smaller than the tool width. We also test our controller on a new unseen tool, where our method demonstrates generalization despite changes in geometry and material properties. Next, we apply our method to a scraping task to remove an object that adheres to the surface. Here, a target object is placed on the table. Additional obstacles are also added in one of the test cases. Again, we specify our desired contact trajectory to move contact through the target object while avoiding contact with the obstacles. Here we show multiple executions on the first test case. Overall, we see that the method is consistently able to remove a majority of the desired material. Next, we show multiple executions for the second case. Note that the tool must be tilted to avoid contact with the obstacles. Again, we see that our method is able to consistently scrape out the target object while simultaneously avoiding contact with the obstacles. Thank you for watching. Please see our paper for quantitative results, comparison to baselines, and further discussion of our method.